this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. This time we're rounding out our study of the nature of galaxies and quasars and active galaxies by seeing how active galaxies and quasars form and evolve. So what is the central engine of an active galaxy? Active galactic nuclei all have one of the same properties. They have very similar properties. One of them is that they're extraordinarily luminous objects. They emit huge amounts of non-stellar energy, meaning the energy source doesn't come from stars. The energy output is extremely variable, and that means it's very small wherever it's happening. And there are jets and other signs of some sort of explosive activity. And around the central engine of an active galaxy, we find broad emission lines with them indicating there's rapid rotation. All right, so what exactly powers an active galactic nucleus? And again, these things have to be explained. The luminosities are on the order of billions to trillions of times, which is 10 to the 9th to 10 to the 12th, solar luminosities. They emit wavelengths all the way from radio all the way to gamma rays. They're extremely compact because the visible light can vary on the order of timescales of a few days, and X-rays can vary on the timescales of hours. So this is really interesting how quickly they can vary in their sizes. So something's got to be small and really bright. So to explain what we see, we use a black hole. The energy source of active galaxies can be usually explained by having accretion of matter onto a supermassive black hole. And by supermassive, we mean 1,000,000 to 1,000,000,000 times the mass of the Sun, which would equate to a Schwarzschild radius of about 1/100th of an AU, up to 10 times 10 astronomical units, meaning the most massive black holes inside of active galactic nuclei, about 1,000,000,000 solar masses, would have a diameter that's larger than the orbit of Saturn around the Sun. So these would be extraordinarily huge black holes. As material falls into it, it releases gravitational energy, and that settles into an enormous accretion disk around the black hole. And when it does so, it gets hotter and hotter and hotter and emits light through friction, and eventually loses that light, and that light leaves the system, and that hot inner part glows, especially in X-rays, right as it's falling into the inner region of the black hole. So just about one or two Schwarzschild radii, it falls directly in. So that's the leading theory about what powers a galactic nucleus, is that, and also when it falls in, the accretion disk spins round and round and round, heating up as it gets closer and closer. And there's magnetic fields that probably appear as part of this disk of material, because most of it, if it's going to be hot enough to emit X-rays, will be ionized and strongly magnetized, and that magnetic field will get wrapped around and create a toroidal magnetic field that can contain material that goes out in a jet. But remember, the black hole itself is extremely small with respect to the jet. And a picture like this is a very good image of what we might see as a jet-like material. So the disk would be surrounding it as material falls in, and as it gets closer and closer, it gets hotter and hotter by friction, and that magnetic field gets stronger and stronger, and you see a jet coming out of the center of it. And so this is the typical picture we see for a supermassive black hole, because even still, something the size of 10 astronomical units is very small compared to a light year, which is very small compared to a parsec. So still, even supermassive black holes are extremely tiny objects, and this disk that we see here would be many hundreds of astronomical units or thousands of astronomical units around. So the central engine can be billions of solar masses, and material that falls in can radiate up to 20% of its mass, in a very weird way of saying. It's not like it's radiating away its mass, it's that the binding energy of the black hole, as material falls into the black hole, the energy that's released is binding energy for the black hole. And so the black hole itself has less mass than the material that falls into it, and some of that gets radiated away. If you were to take the material that's there and spread it back out, it would gain that mass. So it's a sense of saying, where do you get that energy from? And the energy happens to be as a result of falling into a gravitational field. Black holes are extremely efficient at transforming matter into energy. Up to 20% of the rest mass of the particles are converted into light. And then that means that roughly a solar mass per year of matter is needed to power the brightest of the active galaxies, and they get their fuel from surrounding gas and stars, as we saw in that previous image. So you get this a rapidly spinning black hole acts like this enormous particle accelerator, and that creates these incredibly large jets that are seen in active galactic nuclei that are very bright in radio sources. So that gives us kind of our model for active galactic nuclei. You have three different types. You have a normal galaxy with kind of a bright core that might have a supermassive black hole in the core, but it's not really doing anything. A galaxy that has an active galactic nucleus has material that's falling into the supermassive black hole. But then we've got a third thing, the quasars, which are very strong active galactic nuclei that they're so incredibly powerful that they actually overwhelm the light of the surrounding galaxy. And those are the quasars. So let's look at a little bit closer towards them and see the observational evidence for all of these things that lead us to think that there's actually a supermassive black hole down in the center. If we look at this particular one, this is taken by the Hubble Space Telescope of NGC 4261, we see a dual image. The Hubble Space Telescope is the inset on the right-hand side, but it's also inset with respect to a visual light image and a ground base, as well as the radio observation of radio lobes. So we're going to piece apart each one of these things. First of all, this is an elliptical galaxy, as you can see in the left-hand side image. This thing's about 100 million light years away, and so the diameter across this thing is approximately 88,000 light years, or about 100,000 we just call it about 100,000 light years long lobes, and it's part of part of a galaxy group. Now, this particular black hole is roughly 400 million solar masses, and the disk on the right-hand side in the Hubble image shows something that's about 800 light years wide. So that's what that disk is, that's material that's falling into it. The galaxy itself is only about on the left-hand side, the whitish galaxy is about 60,000 light years across. But the jets go each about 88,000 light years along, the length of each of these jets. So you've got radio emission from the jets, you've got stellar emission on the left-hand side. The radio emission is in yellow on the left-hand side. The inset is an incredibly detailed, tiny image of just the core, the inner 400 light years or so. So the disk itself is about 100 light years across. And you can see that there's some extraordinarily bright emission happening inside the center of that disk, and where that lands in there, even still that tiny dot that's there, the black hole itself would still not be visible because it's much smaller than that dot that you see in the center. However, as material falls in, it gets entrained inside of the supermassive black hole, and that is the source of the jets that you see on the left-hand side. All right, so another more local black hole, which is, this one's about 100 million light years away, but something a little bit closer, about 70 million light years away, is the supermassive elliptical galaxy M87 in the Virgo cluster. Now this is the core of M87, and if we look at this is a gaseous, so there's a huge amount of gas that's orbiting it at very high speeds. And so if you take spectra of the gases that are orbiting it, you get two different versions of it. They're on the left-hand side in the image, the spectra is in red, and it shows it's receding away, therefore it's a longer wavelength. And the right-hand side shows that it's rushing towards us, or it's blue shifted. So this is hydrogen gas as it's falling into it. And the light is either blue shifted or red shifted strongly, depending on where we take our measurement of our spectrum. So and by looking at that, it tells us how fast things are. We know the distance to M87, so we can know the size scale of this object because we know the angular size scale, we know the distance, so we can get the physical distance between those two little circles. And that shows us by Kepler's laws that by Newton's version of Kepler's laws, that the mass of the black hole inside of there is between, say, 4 and 6 billion solar masses, which is one of the largest supermassive black holes that is known. And that rotating disk is roughly perpendicular to a known jet of material. And these, in order to have the lines separated out from, as we see from this Hubble Space Telescope's image with the faint object spectrograph, is that the disk itself is rotating at about 1,000 kilometers per second, and that's just under 1% the speed of light. So this is, and it spans about about a third of a light year, about almost a quarter, almost a half a light year. So it's going extraordinarily fast around in this massive wind. So in order to power what we see, the gas is accreting on top of the black hole at roughly 1 solar mass every 10 years, or 90 Earth masses every day. So this supermassive black hole would swallow 90 Earths a day in order to show the emission that we see here. So this is the jet that's emanating out of the M87. You can see the jet in the inset, and there's the Hubble image that we see from it. So we have an inner region and then a jet coming out of it. And that jet is the jet itself is incredibly large, and there's probably the jet is probably occurring at about 7 parsecs away. That's where we see the jet occurring. But the displacement is not really real. It has to be happening right there, but the visible portion of the jet starts happening there. So it doesn't actually start to emit light until it's far away that we can see. But the base of itself, at the base of the jet, right down near the supermassive black hole, the base has to have a diameter of about 5 times the Schwarzschild radius of the black hole, and that supermassive black hole is powering it there. You can also take a spectrum of that jet and just the jet and learn that it's polarized. And if it's polarized, then there must be a strong magnetic field. So you have relativistic, meaning things going nearly the speed of light, in a strong magnetic field in order to polarize the light. What's amazing about this particular jet is that the total energy in the electrons that must be in this jet in order to make this is approximately 10 to the 13th times the energy produced by the entire Milky Way from all the stars in the Milky Way. 10 trillion times the Milky Way's emission in order to get the amount of energy found in this jet, which is a staggering amount of energy, all coming from there. So the center of this thing is brighter than all the Milky Way, all the energy in these electrons, which looks very wispy, but it's not. The energy is extraordinary. And the jets themselves extend up to hundreds of thousands of light years. So what can we see that's doing this, that's creating the energy content of of trillions of Milky Way galaxies inside of this kind of thing? Well, we can see that there's different ways of viewing active galactic nuclei. If you look at it from down above, you see that you're going to see along the jets, and you're going to see very strong X and gamma ray emission, and that's what you see if you're looking from above down. You'll see a jet coming towards you with lots of X-rays and gamma rays. Or if you look at it from the side, you'll just see the jets and a strong infrared emission, because you're not going to be able to see the central X-ray, gamma ray emitting area. But you will see the jets, and you'll see some strong infrared because of the material that's in the disk itself. So so we get broadband radiation, meaning lots and lots of different X-rays from radio all the way to X-rays. But if you only see the jets and only mostly infrared, then you're looking along the edge of it. So one engine can provide lots of different ways of seeing active galactic nuclei. And that's another way of looking at these particular objects, because some of them are radio lobes and some of them are radio cores. But if you see, looking down the radio lobe, you can see if you see just an active galactic nucleus that's just a blob of radio emission, then you're looking straight down the lobe. Straight down the jet. But if you see it from the side, then you can see both the jets and the lobes, and that explains the appearances that we see for active galactic nuclei that we saw in the previous lecture. All right, so what does it look like close up to one of these things? Well, if you saw it, then you'd see a huge amount of material falling in, and as it fell in, things would be taken away in the jets, and if we ride along with the jet as it goes out at many times the speed of light, we would then see some enormous emission from the side. So there's material that's falling into the supermassive black hole. A huge magnetic field creates a jet-like structure, and material comes out of that jet-like structure. And if you look down the jet, you see huge amounts of X-ray and gamma rays. And the X-rays themselves are being produced deep towards the core, and that's what we get to see as the jets from the side. All right, so if we then, here's kind of the model, is an accretion disk around the supermassive black hole. Remember, the supermassive black hole is pretty small. It can be on the order of an astronomical unit or a few, or just like a tenth of an astronomical unit up to 10 astronomical units. So the diameter of where all the action is very small compared to the rest of the galaxy, which would be tens or hundreds of thousands of light years across. So the supermassive black hole and all the energy that's coming from it is coming from an extraordinarily small area. And if there's very small variability, then that's what explains it, because the size scales can vary on the length of a day or two, and that's roughly the size scale of roughly 10 to 40 or astronomical units. So if it's going to be coherently changing, then the entire disk must change. And if the disk is on the order of tens or so astronomical units, that's what we see. Now, the X-ray emission comes from even tighter in, which then, if it can vary on the order of a few hours, which is what we would see if it's on the order of a couple of astronomical units. So X-ray emission comes from deep in the center, and coherent changes come from the entire disk itself. And this one model then can take care of all of the known variability of all active galactic nuclei. And as an example, we can look at Centaurus A. It's one of the nearest galaxies to us. It's only about 10 or roughly 15 million light years away. It's a close radio galaxy, and it's also the fifth brightest galaxy in the sky. So there's lots of observers in the southern hemisphere that get a chance of that. So the supermassive black hole down in the center of Centaurus A is about 55 million solar masses, not as big as M87, 70 million light years away. And those jets that are occurring out of it, those are responsible, and the supermassive black hole emits a huge amounts of relativistic jets, and they create X-rays, which you see in purple, as well as radio light, which you see kind of in the kind of background glow. Now, you can also see if you take radio observations over a few decades or so, a decade or two, you can see that things are actually moving, and the movement inside of the material in these jets is about half the speed of light. And as they move, the jet collides with gases in the surrounding medium and creates very high energy particles, which then decay and form light. So the X-ray jets of Centaurus A are thousands of light years long, and the radio jets that are also visible in other wavelengths can be up to 1 million light years long. So we're only looking at the X-ray jets, but if we could see the radio portion of this thing, it would stretch over 1 million light years long. It'd be much, much, much larger than the full moon. It'd be quite interesting in the sky. So this is also thought to be, of course, a supermassive black hole down in the center with about 55 million solar masses. And here's another view of that. There's the central active galactic nucleus down in the core, and the jet which is coming out the side. These jets are going about half the speed of light, extending for tens of thousands of light years, or thousands of light years long. That's how long that jet is. And there's even the faintest hint of a counterjet. So that's kind of what we would expect in these things, is there'd be two jets, one above the disk and one below, in the center of Centaurus A. And so we see there's the galaxy emitting all of that light. And supermassive black holes and their active galactic nuclei do the trick. All right, so here's another example of an active galactic nucleus. And so this active galaxy has a supermassive black hole in the center, creating all the light. So let's see how the X-ray radiation is occurring specifically in that. So if you have a strong magnetic field, then what happens is you can then have the electrons spinning very, very, very fast inside of this magnetic field. And where the X-ray emission comes in these jets is that as the electron spins and it approaches a proton, because it's going nearly the speed of light. So as it's going nearly the speed of light, it will spin by a proton, and as it does so, feels the pull of the proton while it's moving in the magnetic field, And it loses a little bit of energy. And as it loses some energy, it loses it in the form of light, called an X-ray. So this is called breaking radiation or Bremsstrahlung radiation. And so that's where the X-ray emission comes in these jets as the protons and electrons interact along the magnetic field, and then the X-rays then get emitted as the electron slows down as a result of getting close to the proton inside the magnetic field. And so that's where we get that, and it's called synchrotron radiation. And synchrotron radiation is a result of movement of the electron inside of a strong magnetic field. The X-rays come from the breaking radiation, but then that's a non-thermal form of radiation, as well as what you see from the radio emission. The radio emission is from synchrotron radiation, just from the electrons themselves losing a little bit of energy as they spiral around the magnetic fields. Occasionally they get close to a proton and do the breaking radiation to emit X-rays as well. So therefore, when we look at an active galactic nucleus, we should expect a lot of radio emission, a lot of X-ray emission, and not as much thermal emission. And that's what's being described by the little sketchy graph on the right, is that if it were due to thermal radiation, meaning hot something, then you'd expect kind of a bump like you see there. However, you don't see that. You see a roughly flat emission across much of the spectrum, and then you get lots of radio emission, and then and also some X-ray emission as well from synchrotron radiation. And just to highlight that, a nearby quasar, 3C273, which is about a billion light years away, a billion light years away or so, has three major components, and the center hump, right around 10 to the minus 6 electron volts, that's the thermal emission from the galaxy itself. And at higher energies on the right, that's X-ray emission due to Bremsstrahlung or breaking radiation I talked about. That's what that jagged pointy thing region on the right is due to. And on the left is radio emission due to synchrotron radiation. So notice that both the radio emission, which is synchrotron, and the X-ray emission, which is breaking radiation, have roughly the same kind of shapes to their curves, but they contribute differently. One contributes at high energy on the right, and that's what the dots are. Those dots are the actual measurements of the X-ray radiation. And on the left side, where that peak is on the left, that's the radio emission due to synchrotron radiation. So you have thermal emission from the stars and starlight, but the vast majority of the energy actually comes in the form of X-rays and radio, and almost very little of it comes from visible light, which is the middle little trying to be there sort of hump that's in the middle. But the vast majority of the energy comes from those other regions. And all of that energy from either side of it comes from the supermassive black hole in the center. So we've got this massive, this jet. Things are falling in, creating huge amounts of energy, and it spirals and falls into the central black hole. The black hole heats it. The energy that it's released by getting closer and closer and closer through friction. The friction then heats the gases up to millions of degrees to form X-ray light that we see if we're looking down the top of the jet. And if we can see the jet, then the jet is giving us two different forms of light, one in X-rays as the electrons spiral in the magnetic field and interact with protons, and then there's also radio light from the synchrotron radiation as the electrons themselves just lose a little bit of energy as they go nearly the speed of light as they spiral along the magnetic fields. So they get launched from very close inside of the black hole, and then they spiral along those magnetic field lines constrained in the jet. So then how do these supermassive black holes form? Nobody really knows, but there's probably some collisions between smaller black holes, because there aren't very many middle-level black holes. There's like stellar mass black holes, there's neutron stars. We know that neutron stars are formed by the explosion of supermassive stars. We know that stellar mass black holes up to 100 or so solar masses can be formed by the collisions of either smaller black holes or directly created by massive stellar explosions. But to get a black hole between 100 solar masses and 1 million solar masses, hard to know where those actually come from. So one would think that million solar mass black holes don't just appear out of nowhere. They should grow from something. But to actually not see too many of these intermediate solar mass black holes is a problem for astronomy, and it's an area of active research. Is where are the intermediate solar massive black holes? Because we find stellar mass black holes, and we find supermassive black holes, but not much in between. And actually discovering smaller black holes in between is a definite area of research. So perhaps galaxy interactions, so you have colliding gases. If you have two galaxies colliding, and then they might dump material into the black hole. Or maybe the stellar bars themselves. Maybe we saw barred galaxies. Maybe that itself, the bars themselves, provide a train by which they can funnel into the gas. And maybe smaller galaxies get cannibalized by bigger galaxies. So a huge galaxy is there, and a little galaxy gets too close and falls into the core. And so you can have that, but let's see if that actually is something we can see. The NuSTAR X-ray telescope, which is the next generation X-ray telescope launched by NASA, was able to see on the left-hand side the image of in very high energy X-rays as material falls into the very inner regions of a black hole. That's what this NuSTAR is looking for. It's called a black hole telescope, because if you're looking extremely high extremely high energy X-rays, then those things must come from the inner regions of the black hole. So that's what we're seeing on the left-hand side. Optical images on the right and a combined images in the middle. So the X-ray data says that we're having an enormous, huge galaxy collision, a pair of galaxies colliding, and as they collide, they're forming another massive, supermassive black hole. So there's the X-ray emission just from the NASA's NuSTAR, or Nuclear Spectroscopic Telescope Array, looking at ARP 299, and they weren't sure if one is going after the other, but we're looking specific. Well, there's two black holes colliding inside of this, and if we overlay that with the imagery from an optical image, we can see that the two galaxies, as they're colliding, we see that the X-ray emission comes from the center of them, which is interesting. So the black holes might be in the process of colliding and forming one big black hole. So do most galaxies have supermassive black holes? And the answer is yes. Nearly all spiral galaxies show some level of activity, even the Milky Way. And as we look closer and closer at them, the more we look at galaxies, we find that there's more and more reasons to think that all galaxies have supermassive black holes. If it's a spiral galaxy, it has a supermassive black hole. If it's a massive elliptical, it has a supermassive black hole. In fact, there are no galaxies found yet that don't have supermassive black holes, but the active galactic nucleus element is if there's fuel. So there are lots more AGNs in the past, but fewer today, and where are all the dead quasars? And so that asks the question. Now we see that we find this is just another example of what we mean by this, the size scales of these things. We see them in distant galaxies. Again, another way to look at it is there's other spiral galaxies. When we look at the center of it in 21 centimeter radiation, which is radio light, we can get a Doppler shift and actually see the sides and see the radiation coming from the inner quarter of a parsec of the center of this galaxy, which is approximately 20 kiloparsecs across. And the whole galaxy is more like 10 kiloparsecs across. And the center 0.2 parsecs has super speeds going around. And the super speediness has massive redshift on one side and massive blue shift as material goes around the central supermassive black hole. So such studies of the centers of galaxies, amongst many of them, and then comparing them to others, show that the central mass of a black hole is correlated to the size of the galactic core. So the more massive the bulge of the galaxy, meaning the more massive the black hole. And so that's what this graph means. We can see that smaller galaxy bulges, which are represented by these little dots, have smaller supermassive black holes. Larger galactic cores or galactic bulges have larger supermassive black holes. So there's just basically more stuff to feed on, and the black hole collects more and more stuff. So even though the black hole is an incredibly tiny target, it's like having a target the size of one person across the entire city of New York City, all 5 boroughs. And so the bigger the guy at the center of Times Square, the bigger the city. So imagine that there was a correlation. The weirdness about this is that, let's say you said, well, how big is a city? And then you'd say, well, let's see, there's 10,000 people in this city, there's 100,000 people in this city, and there's 1,000,000 people in this city. What this is saying is, go to the center of that city, and if you find a 1,000-person city, in the very center of the city, you'll find a very small person, like a tiny person. Now, he'll look like a certain thing, and he'll have like a little sign around saying, I'm the center guy in town. But if you go to a larger town, that person will be physically larger. And you'll have a sign and say, I'm the center guy in town. And if you go to a massive city, the guy in the center will be even bigger. But not like giant-sized. The difference in size between them will be maybe 100 times in certain size. But the bigger the city, the bigger the person at the center of the city. And there's a direct correlation between the two of them, which is very interesting. So that tells us something about the evolution of galaxies and black holes in them. So let's see if we can figure out if there is a link between the evolution of galaxies and their active states. So if we then look at the most active of the active galactic nuclei, quasars, quasars were things that are incredibly bright active galactic nuclei. They are the brightest of the AGNs, but they're also the most distant. And therefore, since they're the most distant, they occurred the longest time ago. So therefore, they represent an early stage in galaxy development. So quasars are a long time ago, and if the universe is only 13.6 billion years old, and we're looking billions of years in the past, this is a childhood picture of supermassive black holes. So we can see that the image that we see inset is that quasars are part of galaxies, but yet they're bright supermassive cores of galaxies. Now, quasars themselves then had an epoch where they lived and when they were born and when they died. They seem to have started roughly about 12 billion years ago and seem to have had their peak about 10 billion years ago. And then they kind of petered out after that until about 2 billion years ago. So what we find is that the thing that we call quasars, or whatever is making it the brightest possible thing that the quasars are, that fuel for quasar activity happened when the universe was only a couple of billion years old, a few billion years old, and then it faded away. And so as time went on, fewer and fewer quasars existed until today. We don't have any quasars in the local universe. It doesn't mean that the supermassive black holes have gone away. It's just that there's nothing left to feed them. So supermassive black holes grew, got fed, did their quasar thing, and then stopped. So we look at something like the 2DF Quasar Survey. They just finished this up in 2008, which is a long field survey. We can look at this thing and say, okay, these pizza slices are 2 different directions in the sky, a few degrees wide, high. We just compress it so it looks like a 2-dimensional survey. But the center of this wedge is where we are in the Milky Way, and then we look out into the pizza wedges towards the edge of the pizza, and we find that the peak of them ends at about 10 billion years ago, at a redshift of about 2. But then we see that there are some quasars that approach to about 2 billion light years. But if you squint really hard at this thing, you can say the vast majority of the quasars were between, say, 13 billion years ago and about 10 billion years ago, and then they fade roughly away. Notice that there are fewer by number inside of the 8 billion to 2 billion area compared to the 10 to 12 billion area. There's a lot more that are seen at 10 billion light years away or 12 billion light years away than nearby. So, and there's almost none. In fact, there are none within 2 billion light years of Earth. So that's an important element of it that says that quasars are a temporary process inside of the history of galaxies, and they fade with time. That doesn't mean the supermassive black hole goes away. It doesn't disappear. It's just that the thing that makes a quasar stops after a while. And let's see how that then all adds up. So we have black holes are supermassive and they're part of galaxy evolution. So we're going to find that galaxies start, or we have found and have seen, that little tiny galaxies long, long ago were tiny and misshapen and irregular. And then they merge together. We've seen that galaxies collide and stick together. We've seen galaxy mergers all throughout. And when they merge, they make a larger central black hole. Those then go from tiny misshapen galaxies to larger galaxies with some sort of central black hole. Then those things collide and the black holes fall together to form supermassive black holes. Now when you have two large such galaxies colliding, you then have an enormous amount of material that forms them, and that can create a radio galaxy or a blazar or a quasar across the top. And but if we're looking straight down the top, there's a huge amount of material. That active galactic nucleus then can be a radio galaxy, a blazar, or a quasar, and then eventually that settles down, using up all the gas and dust and material, and it blows everything out, and it eventually settles into becoming an elliptical galaxy. However, the quasar activity occurs, and then after it does the quasar activity, it has little bitty tiny other mergers. Then you can get Seyfert level activity after the quasar is done, because quasars are a very short period of time when suns are being consumed per year, because that's what the amount of energy that it takes to make a quasar. So quasars themselves fall with, when they're done doing quasar activity, you have a normal galaxy, and if they have little tiny mergers, then you can have Seyfert level activity, which is a lot of active galactic nucleus, but you don't get the lobes or blazar activity, but just little activity, and then those things can settle down and become spirals. But if you have massive activity, it can disrupt and use up everything in the entire galaxy, blowing away the gas and dust and eliminating it, forming giant elliptical galaxies such as M87. Or you can have a series of minor mergers and form spiral galaxies such as M101 or the Milky Way. And that's our summary of exactly how galaxy evolution and those things go. So supermassive black holes can explain that, and they can also explain the evolution of galaxies as they go from billions of years, as they can evolve by collisions and mergers into forming larger galaxies. All right, so we're going to go into the cosmological end of things next time. See you soon.